Having learnt a little bit about some equilibrium concepts, we're now able to go back and have another look at the end of chapter 16, 16.4, and discuss how these concepts are related to the free energy changes accompanying a reaction. So you may recall in chapter 16 in Chemistry 162, we stated that if the Gibbs free energy change for a reaction is less than 0, a reaction will proceed spontaneously to the right-hand side. And conversely, we also said that if a reaction has a positive Gibbs free energy change, it will not spontaneously move to the right-hand side. Now, in chapter 13, we were learning that there was another way of predicting if a reaction will proceed spontaneously towards products. And it's pretty simple, isn't it? If Q is less than K, the reaction will spontaneously move towards the products. And if Q is greater than K, the reaction will spontaneously move towards the reactants. So it seems that both delta G and Q are indicating the direction of spontaneous change. For that reason, these numbers should be relatable in some way. So a reaction will proceed spontaneously until delta G equals 0. At that point, there is no net movement towards either reactants or products. That is, the system will be at equilibrium. So what this really means is, an alternative way of stating this is that a reaction will proceed spontaneously until Q equals K. That is, when delta G equals 0, the system is at equilibrium and Q equals K. So delta G and Q are both measures of how far a system is from equilibrium. When delta G equals 0, the system's at equilibrium. When delta G doesn't equal 0, the system is not at equilibrium. When Q equals K, the system's at equilibrium. When Q is not equal to K, the system is not at equilibrium. So, if we work through the math, we can see that the relationship between the Gibbs free energy change and Q is given by this equation. The Gibbs free energy change for a reaction is equal to the standard Gibbs free energy change plus RT log Q. And the degree sign there indicates that this is the Gibbs free energy change under standard conditions. So that means that everything has a concentration of 1 mole per liter, and all gases have a pressure of 1 atm. Now, recall that using the values that are in the appendix, it's actually appendix G, and this formula here, we can always calculate the standard Gibbs free energy change for a chemical reaction. So all we have to take note of is the standard Gibbs free energy change of a reaction is equal to the sum of the Gibbs free energy of formations of all of the products minus the sum of the Gibbs free energy changes of formation for all of the reactants. So you're just going to do products minus reactants. Now, when the system is at equilibrium, delta G equals 0 and Q equals K. So, going back to our equation that we presented previously, we said that delta G is equal to the standard Gibbs free energy change plus RT log K. Now, if we are at equilibrium, then Q is equal to K and delta G is equal to 0. So then we could say that 0 is equal to the standard Gibbs free energy change plus RT log K. Or alternatively, we can say that the standard Gibbs free energy change for a reaction is equal to minus RT log K. So what this really means is if I have the standard Gibbs free energy change for a reaction, I can get K, and vice versa. If I have K, I can get the standard Gibbs free energy change for my process. So let's have a look at an example problem. It says use the following data to calculate Kp for this reaction at 298 K. So the K we're trying to calculate is N2 combining with O2 to make NO2. And these are the two reactions that we have. And for each reaction, we have the associated Gibbs free energy change. So we're going to see if we can add these things together to get our overall equation. And I hope what you see is if you simply add this equation and this equation, then you get the one that we want, because this will cancel out. And then what we're left with is N2 plus 2O2 in equilibrium with 2NO2. Now, the delta G for this is simply going to be the sum of my two delta G's for my two reactions. So we can put that into our calculator, and we get 103.3. So now we know the delta G for our reaction. So delta G naught for this guy is 103.3 kilojoules. So this is our equation that relates delta G and K. So we can reorganize that to get log K. Make certain that you enter your values as joules, not kilojoules. And then your R needs to be 8.314 joules per mole per Kelvin. So whenever we're using R in an equation with energy, we're always going to use 8.314. And then our temperature it was given in the problem is 298 K. So we put all of that together and log K equals negative 41.69. So to undo the log, we have to take E of that value. And then here is our K value here, 7.81 by 10 to the minus 19. So a very small K value, which indicates that this is not a very favorable reaction, which is consistent with our positive delta G. So positive means that it favors the left-hand side, not the right-hand side. So that all kind of makes sense. Okay, so we had previously noted that K is dependent on temperature. If we have an endothermic reaction and we raise the temperature, the system will shift towards the right. And a good way of seeing that is in this reaction here, where we have one of our reactants, cobalt hexachloride 2+, which is pink, reacts with chloride ions when we heat it up to make cobalt tetrachloro di-negative anion, which is blue, and water. So if we take this pink stuff and we heat it up, in this case we heat it up by 70 degrees, it'll turn blue. If we cool it back down, it'll turn pink. So we can see that K is getting bigger and smaller, and we do this reaction in the lab and it's kind of fun. This is all qualitative, right? This is all qualitative. The question is there a quantitative way of expressing how K depends on the temperature? And the answer is yes. So in chemistry 2, we learned that enthalpy changes, entropy changes, Gibbs free energy changes, and temperature are all related by this equation, delta G equals delta H minus T delta S. But now we know that delta G is equal to minus RT log K. So now we can insert minus RT log K wherever delta G occurs. So that's what we're going to do here, putting that into our equation that we have at the top. And then now we can reorganize and get a form that's of y equals ax plus b. And we end up with this. Log K is equal to negative of delta H on R multiplied by 1 on T plus delta S on R. And so what does this mean? It means if we plot log K against 1 on T, we'll get a straight line. So if I plot log K against 1 on T, according to my equation, I'm going to get a straight line with slope negative delta H on R and intercept delta S on R. So that's, kind of helpful. If I was to determine K at a series of temperatures, I could get delta H and delta S Similarly, if I had delta H and delta S, I could get K at a particular temperature. Now, this sort of point-intercept form, this linear form of the equation, is useful if I wanted to make a graph, but what I can also do is reorganize this equation to get what we call the two-point form. So I'll show you what, this is kind of similar to what we did with the Arrhenius equation. So I won't go through the math because we've done this before for the Arrhenius equation, but we can rewrite this expression in the two-point form, which is log K1 on K2 is equal to the negative of delta H on R multiplied by 1 on T1 minus 1 on T2. Now, this formula is known as the Van Hoff equation, and you won't actually find that term in the book, but if you're trying to Google information about this, that's going to help. That's going to be the term you're going to want to look up. And you can see that it has a similar form to the two-point form of the Arrhenius equation, and also it looks very, very similar to the Clausius-Clapeyron equation, which we saw in Chemistry 162. Now, it's important to realize that the reason that it looks like the Clausius-Clapeyron equation is because it's actually just the more general case of that system. So the Clausius-Clapeyron equation is a special case of the Van Hoff equation where we're looking at the vapor pressure of a gas above a liquid. So for that scenario, we have a liquid in equilibrium with its vapor. The enthalpy change for that reaction is equal to the enthalpy of vaporization, and the K for this reaction is just equal to the partial pressure of our vapor, because we don't include liquid terms in our expressions for K and Q. So in this case, our Van Hoff equation, log K1 on K2 equals minus delta H on R multiplied by 1 on T1 minus 1 on T2, simply becomes log of P1 on P2, because K is just equal to our vapor pressure. And as our enthalpy change is equal to our enthalpy of vaporization, this will be equal to the negative of the enthalpy of vaporization over R multiplied by 1 on T1 minus 1 on T2, which is our Clausius-Clapeyron equation. So let's look at an example of how we might use this formula. So this problem reads, at 600 K for the following reaction, Kc equals 1.7 by 10 to the 8. So that's telling us that this reaction lies very much to the right. The reaction is 2SO2 reacts with 1 O2 to give 2 SO3. The problem continues. An engineer places 0.004 moles of SO2 and 0.0028 moles of O2 in a 1 liter container and raises the temperature to 1000 Kelvin. So it's important to realize that to begin with, there is no products present. At equilibrium, 0.002 moles of SO2 is present. Calculate the enthalpy change for the reaction. So what we're going to do is we're going to calculate the K at 1000 Kelvin using the data given. We have another K at 600 Kelvin given at the start of the problem. So if we've got two Ks and two temperatures, we should be able to solve for the enthalpy change of the reaction. So I'm going to go ahead and set up the ICE table for the 1000 Kelvin data. So we started with 0.004 moles per liter of SO2, 0.0028 moles per liter of O2, and we had no SO3 present. So the system is going to move towards SO3. So that means that the SO2 will go down by 2x, the O2 will go down by 1x, and the SO3 will go up by 2x because there are two of those in our equation. So when this comes to equilibrium, we were told that the SO2 will have a concentration of 0.0020. So that means it went down by a half. So let's calculate what what X is. So 0.004 is what we started with. Then the SO2 went down by 2x, and we ended with 0.0020. So solving for X tells us that X is 0.0010. So we can update our ICE table using our value of X and get all of the equilibrium concentrations for our reactants and products. So we've done that here. Now we can go ahead and calculate K at 1000 Kelvin. So because I've got two SO3s, I have to square my concentration of SO3. I also have to square my concentration of SO2, but I don't need to square or cube my concentration of O2 because I've only got one of those guys. So putting in my equilibrium values into my expression for Kc, I get my new value of Kc at 1000 Kelvin. So now I have a value of Kc at a lower temperature at 600 Kelvin, a value of Kc at 1000 Kelvin, so I should be able to solve for delta H. So I've got log K1 on K2 is equal to negative delta H on R multiplied by 1 on T1 minus 1 on T2. So if I reorganize everything to get delta H isolated, I'm just going to multiply both sides by minus R and then divide by this 1 on T1 minus 1 on T2 term. That'll give me delta H. So I'm going to put all my numbers in. R is 8.314. K1 is 1.7 by 10 to the 8. And then K2 is the value I just calculated, 556. So worth noticing that as the temperature went up, K went down by a lot. So that tells me that this reaction is endothermic. So put my two temperatures in, 1 on 600 for 1 on T1 minus 1 on 1000 for 1 on T2. And then now calculate everything and I got a big negative number. This is going to be in joules because of the units for R. Converting to kilojoules by dividing by 1000, it tells me that it's got an enthalpy of negative 158. And that makes sense because we know that this reaction must be exothermic. So yeah, it's cool, right? Everything looks like it's working the way that it's meant to. So if I have two temperatures and the corresponding Ks, I can always get delta H. Okay, so that concludes section 16.4, or really the part of section 16.4 that we had to go back and finish off. We found a way of relating Q and the Gibbs free energy change for a reaction. We then went on and defined how we can relate the standard Gibbs free energy change for a reaction and K. And then finally, we developed the Van Hoff equation that allows us to determine the enthalpy change for a reaction if we have two Ks at two different temperatures.